Welcome to the class. Today we are going to talk about turbojet engine, its configuration and its example, how to deal with an example of turbojet engine. Turbojet configuration, as we know, turbojet, if we plot in schematic, it would have first an intake, there would be an intake, after the intake there would be compressor, air will first come into the intake, then it will go to the compressor, and then after the compressor it will go into the combustion chamber or burner, after the burner it will go into the turbine, which is basically the gas turbine for us. Then after the turbine it will go into the nozzle, and then here it generates the necessary velocity, which is Cj, where entering velocity is Ca, and then we generate the thrust basically, which depends upon Pj, Pa and Cj, Ca and also m dot. So we know thrust is equal to m dot A plus m dot F into Cj minus m dot A into Ca plus Pj minus Pa into Aj. So this is the expression for thrust which we need to calculate for the turbojet engine. So we would know how to find out the properties in the intake. We know that there is ram efficiency or isentropic efficiency of intake. It governs the compression which is achieved before the air it reaches to the compressor. Then there is compressor efficiency, which is telling us that if a compression in the compressor is not isentropic. There is combustion chamber efficiency or burner efficiency, it does not release the complete chemical energy of the fuel, but some energy is lost. Then there is turbine efficiency, which tells us that process is not completely isentropic in the turbine, but it has certain losses. There is one more efficiency, that this turbine and compressor, they are connected with each other, and then that efficiency is called as transmission efficiency, where the power generated from the turbine is given to the compressor and some of the power is getting lost. So we have to give extra power, which is going to account for the transmission loss. If Wc is the necessary work input for the compressor, then we have to produce the work which is more than the compressor work. So this should be equal to turbine work. So turbine necessarily present in the turbojet to run the compressor. In ideal case, turbine work is equal to compressor work, but due to transmission losses we have to do more work in the turbine, such that we can produce necessary compression in the compressor by supplying the work. Then we have Nj, which is nozzle efficiency, where the process is not reversible in the nozzle and it leads to the losses in the nozzle. So the whole idea in case of turbojet is different from the shaft power cycle what we had seen, where the whole objective was to find out W net. Here objective is to find out thrust or specific fuel consumption, and we have seen the formulas about these quantities. So, for given condition of the turbojet, we are supposed to find out the thrust or specific fuel consumption, or maybe the necessary quantities. Most of the components like turbine, compressor, combustion chamber would remain same in other turbofan engine also, but in principle this is the composition for a turbojet engine. Let us proceed with an example which states that a simple turbojet unit operates with a maximum turbine inlet temperature of 1200 Kelvin and a pressure ratio of 4.25:1 and mass flow of 20 kg per second under design conditions. Following component efficiencies may be assumed. Isentropic efficiency of compressor is 87%, isentropic efficiency of turbine is 91.5%, as propelling nozzle efficiency is 96.5%, transmission efficiency is 98.5%, combustion chamber pressure loss is 0.21 bar. Assume specific heat of air as 1.005 kilojoule per kg Kelvin, specific heat of air as 1.4, specific heat of gas as 1.47 kilojoule per kg Kelvin and specific heat ratio for the gas as 1.33. Calculate the total design thrust. Also calculate the total thrust and specific fuel consumption, taking into account or taking into consideration the nozzle choking condition. Assume that the unit is stationary and at sea level, where the ambient condition may be taken as 1 bar and 293 Kelvin. Assume air fuel ratio as 50. A notable point in this example that nothing is told about intake, so we can exclude the intake, where we can feel that the given conditions as 1 bar and 293 Kelvin are the inlet conditions to the compressor. So, these are the compressor inlet conditions, and we can proceed with the example. Further, it is notable over here that we are told to use different properties for air and the gas, which is specific heat and specific heat ratio. So, let us plot the TS diagram first before we proceed to solve the example. Here we are at the entry to the compressor, we are at the exit to the compressor, we are here at the point 03 in the combustion chamber outlet, but we are told that there is combustion chamber pressure loss. So, we have to cater that, and then we will be here for P03. So, we are here for 03 and the process is like this. This is not 2 dash, this is not 2, and then expansion in the turbine is isentropic. This is not 4 dash, this is not 4, and then further expansion in the nozzle can also be isentropic or need not be. Here it is 5 dash and 5. So, this is what it is required for us to evaluate. Let us start evaluating the corner quantities. We are told that in the given quantities we are given that compressor pressure ratio as 4.25:1, T03 is equal to 1200 Kelvin, m dot is equal to 25 kg per second, and compressor efficiency is 87%, turbine efficiency is 91.5%, transmission efficiency is 98.5%, combustion efficiency or burner efficiency is given, nozzle efficiency is given in this example, where Nj is equal to 96.5% and then delta P naught combustion chamber as 0.21 bar. We know that T02, we know the formula for compressor efficiency is T02 dash minus T01 divided by T02 minus T01, which leads to T02 minus T01 is equal to 1 upon compressor efficiency T02 dash minus T01, which is equal to 1 upon compressor efficiency T01 T02 dash upon T01 minus 1, and then this is related with isentropic relation. So we can have T01 upon compressor efficiency into P02 upon P01 bracket raised to gamma minus 1 upon gamma, which is necessarily the RPC bracket raised to gamma minus 1 upon gamma minus 1. So T01 is given as 293 Kelvin. This is 293 divided by compressor efficiency, which is 0.87 and into the bracket 4.25 and bracket raised to 0.285 minus 1, and this gives us T02 is equal to T02 is equal to 465.6 Kelvin. So this is the value in reality at the exit of the compressor. Now we know that compressor work upon transmission efficiency is equal to turbine work. In this example, we needed the entry total temperature for the nozzle, for which we need the turbine pressure ratio, but we don't know turbine pressure ratio. So we have to calculate the turbine pressure ratio first, for which we are going to use the relation which states that compressor work upon transmission efficiency is equal to turbine work. So we have to be careful here, since in the compressor we have Cp air into T02 minus T01 divided by transmission efficiency is equal to Cp gas into T03 minus T04. We know everything over here except T04. So we can calculate T04. So first T03 minus T04 is equal to Cp air divided by Cp gas into transmission efficiency into T02 minus T01. So we have T04 is equal to T03 minus Cp air divided by Cp gas into transmission efficiency into T02 minus T01. Now we know T03 is equal to 1200, specific heat of air is 1005 divided by same for gas is 985. It is given to us as 1147 into 0.985, which is transmission efficiency, into T02, which we have just calculated, minus T01, which is 293, and this gives us T04, and hence T04 is 1046.4 Kelvin. So this is the total temperature at the exit of the turbine. Now here we can use this total temperature for finding out the pressure ratio for the turbine. Since we know turbine efficiency, we can use this formula as what we used. Turbine efficiency is actual work done divided by ideal work done. So this can be formulated using turbine pressure ratio as what we did in case of compressor. We formulated it in terms of pressure ratio. Here same way we can formulate it for the pressure ratio using this, where we have T03 minus T04 is equal to turbine efficiency into T03 into 1 minus 1 upon turbine pressure ratio bracket raised to gamma minus 1 upon gamma, but here it is should be noted that this is gamma for gas. Now we are just unknown with RPT, which is pressure ratio for turbine. We know T03, we know T04. So from this we can calculate T03 is known, which is 1200, T04 is 1046.4, turbine efficiency is given, which is 0.915 into 1200, 1 minus 1 upon RP turbine bracket raised to 1.33 minus 1 divided by 1.33. We are told that specific heat ratio for gas is 1.33. If we rearrange the terms, we can get turbine pressure ratio as 1.835. So this is the turbine pressure ratio. Now knowing this, we can find out P04, which is the exit pressure of the turbine. We first should know what is P03. P03 is equal to P02 minus delta P0 Cc. So it will be 4.25. We are told that exit condition entry to the compressor is 1 bar, compressor pressure ratio is 4.25. So total pressure at the exit of the compressor is 4.25 and loss is 0.21. So we can know here that 4.04 bar. Knowing this, we can calculate P04 from the fact that turbine pressure ratio RPT is equal to P03 divided by P04. So P04 is equal to P03 divided by RPT. It gives us P04 as 2.2 bar. So now we know what is the exact value of the pressure at the exit to the turbine. In the example, now it is asked to us to find out the total thrust and or other designed value of the thrust. Here we are not going to discuss about the choking condition. The next part of the example deals with choking condition. So let us first resolve the conditions. We know that T04 divided by T5 dash is equal to P04 by P5 dash, which is so we have just now calculated it as 2.2 divided by 1 and bracket raised to P04 by P5 dash, or P5 is equal to gamma minus 1 upon gamma. This is gamma for gas. Considering this, we will get this ratio. Putting P04 as 2.2 and P5 dash as 1, we will get it as 1.21. This ratio as 1.21. Here our objective is to find out T5. Once T5 is known, then we can find out what is the value for the exit jet velocity. But before that, we should know what is T5. From this we can know now T5 dash. T5 can be found out from nozzle efficiency, which says that T04 minus T5 divided by T04 minus T5 dash. So we have T5 is equal to T04 minus nozzle efficiency into T04 minus T5 dash, and then this gives us with all the known quantities the value of T5 as 867 Kelvin. So now we know T5. We can write down the energy equation for the nozzle, which says that H naught, which is the H04 at the exit of the nozzle, total enthalpy at the entry of the nozzle is equal to H5 plus Cj or C5 square by 2. So we have T04 is equal to T5 plus Cj square upon 2 Cp, where this is Cp for gas, So we can calculate Cj from here, knowing the T04 and T5, we can calculate Cj, and it is 641.4 meter per second. Here we have completely considered expansion of the gas to the exit pressure, where we have considered P5 is equal to Pa, which is 1 bar. So there is no pressure component existing in the thrust. So we have thrust T is equal to m dot A plus m dot F into Cj minus m dot A into Ca, but mass of fuel is negligible, then thrust is equal to m dot A into Cj minus Ca, but further Ca is at sea level, there is 0 velocity, so it is m dot A into Cj, and Cj we have calculated, m dot A is given, which is 25 kg per second. So we can get thrust is equal to 16036.6 Newton. So this is the value of the design thrust, where we have considered complete expansion in the nozzle till we attain the exit pressure equal to atmospheric pressure. We did not consider any choking condition. Now let us move on to the next part of the example, which says us that let us consider the choking condition. We had seen that first we have to find out what is the choking pressure, and then based upon that we can work up for the choking condition. Let us continue with the second half of the example, where we need to see accounting choking condition. As per this is the second part. So we have to see whether the nozzle is choked. So P04 upon Pc, this is a theoretical relation which we have developed, which we have derived, depends upon nozzle efficiency gamma g minus 1 upon gamma g plus 1 bracket raised to minus gamma g upon gamma minus 1. So we have P04 upon Pc is equal to 1 minus 1 upon point. Nozzle efficiency is given as 96.5%, so 965 into gamma g is 1.33 minus 1, 1.33 plus 1 minus 1.33 upon 1.33 minus 1. So if we put this, we will get P04 upon P0C is equal to 1.895. So this is the theoretical relation, but we know what is our P04. We have got P04 as 2.2 bar. P04 is 2.2 bar and P0A PA atmospheric pressure in this example is said to be 1 bar. Since it is at sea level, so we have P04 upon PA is equal to 2.2 bar. Hence, we have P04 upon PC is less than P04 upon PA. So PA is less than PC. This says that nozzle is choked. So since nozzle is choked, we have to find out the choking condition. So, or rather exit condition. So exit condition is exit pressure, which is PC, and PC is equal to P04 divided by 1.895, and so we have 2.2 divided by 1.895, and thus gives us PC to be 1.16 bar. Now let us find out TC, which is actual temperature at the exit of the nozzle, but this should be dependent upon nozzle efficiency, and we know nozzle efficiency is T04 minus TC divided by T04 minus TC dash. Here we can represent this as TC dash is equal to 1 minus 1 upon nozzle efficiency into 1 minus TC upon T04 into T04. So TC dash upon T04 is 1 minus Nj 1 minus TC upon T04, but we know this is equal to PC upon P04 bracket raised to gamma minus 1 upon gamma. This is for gases, so this is 1.1895 bracket raised to 1.33 minus 1 divided by 1.33, and this comes to be 0.8533, and hence using this, that is known efficiency of the nozzle, we can find out. Okay, so we can calculate TC from here, where we will say that 1 upon Nj into 1 minus Tc upon T04 is equal to 1 minus 0.8533, and this number would be known to us, and from here we can further go ahead, put the value of Nj, and then we will say 1 upon 0.965 into 1 minus Tc divided by T04. We had calculated T04, it is 1046.4, so it is 1046.4 is equal to 1 minus 0.8533. This gives us Tc is equal to 898.26 Kelvin. Having known this Tc, we can calculate Cj, which is equal to acoustic speed, which is equal to under root gamma RTj or Tc. Since we have Mach number 1, we know here we are not given with R. So first we have to find out R. We know Cp is equal to gamma R upon gamma minus 1. So R is equal to gamma minus 1 into Cp divided by gamma. We are told that gamma is equal to 1.33 and Cp is 1.147. So this gives us R is equal to 284. This is 10 to the power 3, since it is 1.147 is in kilojoule per kg Kelvin. So R in kilojoule per kg Kelvin is 0.284594. So R is equal to 284.59 joule per kg Kelvin. Now this R we can use here, and we can see gamma is 1.33, R is 284.59 into Tc is 898.26. So this gives us Cj is equal to 583.09 meter per second. Knowing this Cj, we could calculate thrust, but before that we have to calculate the thrust based upon pressure. Since this is the thrust, this value will give us thrust only from momentum. So let us write down the formula to calculate area, which is not given to us. We know m dot is equal to rho j Aj into Cj. So Aj is equal to m dot upon rho j Cj. M dot is given to us as 25, and we know now Cj we have calculated, which is 583.09, and rho j is basically Pc upon RTc. So we know Pc, since we have calculated Pc as 1.16 bar, Tc is 98, R is 284. So this gives us Aj, and that comes to be 0.094 meter square. Knowing this Aj, now we can calculate thrust is equal to m dot A Cj minus Ca plus Pj minus Pa into Aj. So m dot, we have Ca is 0, so 25 into Cj is 583.09, Pj is known to us, which is Pc 1.16, atmospheric pressure into 10 to the power 5, since these are in bar, into 0.94. This gives us value of thrust as 16081 0.25 Newton. This is useful to calculate specific fuel consumption, which is m dot f upon thrust. So, let us find out, since we are given with air fuel ratio, let us use that. Let us divide numerator and denominator by m dot a. So, this is given, air fuel ratio is given as 50. So, this is 1 by 50 and this is 16081.25 divided by 25. So, this gives us the value as we have to multiply this by 3600 to get the number in the units of hours. So, we will get 111 kg per Newton hour. So, this is how we can solve the example for the turbojet, where we were supposed initially to find out the thrust if gas is completely expanded or if there is choking of the nozzle. So, let us see for the next example, and next example states that following is the data for a turbojet flying at 805 km per hour speed at an altitude having pressure of 0.458 bar and temperature 248 Kelvin. Combustion chamber pressure loss is given as 0.21 bar. Compression total pressure head or compressor head is given as 4:1. Calorific value of fuel is given as 43,000 kilojoule per kg, which is 43 megajoule per kg. RAM efficiency of intake is given as 95%. Turbine inlet temperature is given as 1100 Kelvin. Efficiencies for compressor, turbine and transmission are respectively given as 0.85, 0.9 and 0.99. Nozzle efficiency is given as 0.95. Assume the nozzle to be convergent with exit area of 0.0935 meter square, and then we are saying that Cp of air, Cp of gas and specific heat ratios of either are given. So, let us solve this example. In this example, as we know, we are having first intake, then we are having compressor, then we are having combustion chamber, then we are having turbine, then we are having nozzle. So, this is atmospheric condition, and then this will be P01, this will be not 1, not 2, not 3, not 4, and then this depends upon the choking and so practically in static this is 5. So, we are told that RAM efficiency is 95%. So, we will use this, and we know how to find out RAM efficiency using the formula P01 minus PA divided by P0A minus PA, actual maximum pressure rise divided by ideal maximum pressure rise. Here we need to know P0A. For that we have to first find out Mach number. So, before that we are given that Ca is equal to 805 kilometer per hour, and this if we convert into meter per second, then we will get it as, this is for kilometer, this is for second. So, this we will get it as 223.6 meter per second. Knowing this, we know acoustic speed in ambient condition is gamma RT, where this is atmospheric, and we have atmospheric air. So, gamma is 1.4 and R is 287, TA is given, and that TA value is 248 putting these values, we will get acoustic speed as 315.66 Kelvin meter per second. So Mach number is Ca upon Aa, and we get Mach number as 0.708. Knowing this Mach number, we know P naught A upon Pa is 1 plus gamma minus 1 by 2 Ma square bracket raised to gamma upon gamma minus 1. So here we know P naught A upon Pa is 1 plus 1.4 minus 1 is 0.4, 0.4 divided by 2 is 0.2 into 0.708 bracket square 1.4 divided by 0.4. So P naught A upon Pa gives us the ratio as 1.3975, and this gives us P naught A as 0.64 bar. We are given with Pa as 0.458 bar. So this gives us P naught A. So we can put this P naught A and find out for the P naught 1. So we are 0.95 from the RAM efficiency, P naught 1 0.458 divided by 0.64 minus 0.458, and this gives us P naught 1 as 0.63 bar. So we get P naught 1 as 0.63 bar. Having said this, now we can move ahead and calculate the other corner quantities for the cycle. So we are told that compression pressure ratio for the compressor is 4. So we know P naught 2 upon P naught 1 is equal to 4. So P naught 2 is equal to 4 into 0.36, and that is 2.52 bar. Now we can calculate T naught 2, since T naught 2 is equal to T naught 1 plus T naught 1 into compressor efficiency bracket raised to RPC bracket raised to gamma minus 1 upon gamma minus 1. We know how to derive this formula from the fact that compressor efficiency is equal to T naught 2 dash minus T naught 1 divided by T naught 2 minus T naught 1. Then if we take T naught 1 common, then T naught 2 dash upon T naught 1 becomes P naught 2 dash upon P naught 1, which is RPC bracket raised to gamma minus 1 upon gamma. Having known this, we can find out T naught 2, but for that again we should know T naught 1, and T naught 1 can be found out being the process as isentropic, being the process as adiabatic in the intake. We can know it as 1 plus gamma minus 1 by 2 Ma square, and so this gives us T naught 1 as 272.86 Kelvin. So we have T naught 2, putting this all numbers here, we can get T naught 2 equal to 429.05 Kelvin. Now we have calculated this and we have calculated this. So let us move and calculate for the conditions for 3 and 4, but we are given with the turbine inlet temperature as 1100 Kelvin. So we are knowing T naught 3, but we do not know the condition at T naught 4. So, but we know that there is a transmission efficiency related with compressor and turbine. So, we have compressor work divided by transmission efficiency is equal to turbine work. So, we have Cp of air into T02 minus T01 is equal to transmission efficiency into Cp of gas into T03 minus T04. So, we have T03 minus T04 is equal to Cp of air divided by transmission efficiency into Cp of gas into T02 minus T01. So, this gives us, we know Cp of air which is 1.001, we know Cp of gas 1.147, transmission efficiency is given as 99%, and then T02 is found out 429, T01 is known which is 272. So, this gives us T03 minus T04 as 138.23 Kelvin. So, we get T04 which is getting subtracted from 1100, and then we have 961.76 Kelvin. Now, what we are not knowing at this moment is the turbine pressure ratio. So, we can know turbine pressure ratio from turbine efficiency formula, where turbine efficiency is T03 minus T04 divided by T03 minus T04 dash. Here we know now T03 minus T04 is evaluated as 138.23 and divided by T03 is 1100 minus T04 dash, but this efficiency is given to us as 0.9. So, knowing this, we can calculate the ideal temperature at the exit of the turbine as T04 dash, and that is equal to 946.40 Kelvin. So, knowing this, we can proceed, but then first let us find out what is P03, but P03 is equal to P02 minus delta P0 combustion chamber, which is given as 0.21 bar, and P02 is 2.52 bar. Since we have evaluated P02, we have got it as P02 we have got it as 2.52 bar minus 0.21 bar. So, it comes to be 2.31 bar. So, we know now P03 divided by P04 is equal to T03 divided by T04 dash bracket raised to gamma gas upon gamma gas minus 1. So, this would be 1100 divided by 946.40 bracket raised to 1.33 divided by 0.33, and we get here P03 by P04 is equal to 1.833. So, this gives us P04, and P04 comes out to be 1.26 bar. Since we know P03 is 2.31 divided by 1.833, this gives us P04 as 1.26 bar. So, we can find out which is the pressure known, total pressure at the entry to the nozzle is known, atmospheric condition is known. So, driving pressure ratio for the existing nozzle is P04 upon PA, which is 1.26 divided by 0.458, and this ratio comes to be 2.751. So, knowing this pressure ratio, we can compare with the choking condition, and choking condition pressure ratio says that P04 upon Pc is equal to 1 minus 1 upon nozzle efficiency into gamma gas minus 1 upon gamma gas plus 1 bracket raised to minus gamma gas upon gamma gas minus 1. Now nozzle efficiency is given to us as 95%, gamma gas and all the other things are known, which as 1.33. Putting those all numbers, we will get P04 upon Pc as 1.91. So here P04 upon Pa, which is 2.751, is bigger than P04 upon Pc. This says that Pc is greater than Pa, so we have nozzle choked. So since nozzle is choked, we have to find out the temperature at the exit of the nozzle for the choking condition. But we know the process is adiabatic from 4 to 5, and then there is Mach number 1 in the exit, number 1 in the exit of the nozzle. Nozzle is adiabatic. So knowing this, we know T04 is equal to T05, which is from the adiabaticness, and this is 961.76 Kelvin. So we can find out T05 upon T5 as 1 plus gamma minus 1 by 2 for gas into m square, but m is 1, so this is just gamma gas plus 1 by 2, so this is 1.65. Knowing this, we can calculate T5, and T5 comes out to be 825.54 Kelvin. Knowing T5, we can calculate Cj, which is again speed at the exit of the jet speed at the exit of the nozzle, which is gamma gas R gas into T5 or Tc. This is same as Tc. Then this is equal to Cj. Gamma gas is 1.33. We have found out R, and then R was 284 in earlier example. In the same way we can find out R here as well, and then Tc is 825.54. Knowing this, we get Cj is equal to 558.99 meter per second. Now what we need to evaluate here is mass flow rate, since we are given with area of the nozzle. So for thrust calculation, we need to know the mass flow rate. So it is rho j, Aj, Cj, but we do not know rho j, which is equal to here rho j is equal to rho c is equal to Pc upon Rtc. So it has Pj upon Rtj into Aj into Cj. So m dot we can use here. Pc further needs to be calculated. So Pc, which is Pj, and that is P04 upon choking condition criteria, which had come out to be 1.9167 into 1 upon 284 into Tj, which is 825 into area of the jet, which is given, and now Cj, which is 558.99, and all these numbers give us mass flow rate as 14.64 kg per second. We have to remember here that P04 should be taken in Pascal. So having known this, we can find out thrust which is T, which is m dot A into Cj minus Ca plus Pj minus Pa into Aj. So, thrust we know m dot now 14.64, Cj is known 558.99, Ca is given 223.6 plus Pj is Pc, which is 0.657, which has been obtained as this, which is P upon RT, which is this P upon RT minus atmospheric pressure is 0.458 into Aj, which is given as 0.09. So, this gives us thrust value as 6770.75 Newton. We also need to calculate specific fuel consumption, and then that specific fuel consumption can be found out. Before that, we have to find out mass flow rate of fuel. So, for that we can apply energy equation. For the burner, we will have m dot F into QCV is equal to m dot A Cp gas into T naught 3 minus T naught 2. So, m dot F is equal to m dot A into Cp gas T naught 3 minus T naught 2 divided by calorific value. We have calculated T naught 3, we have T naught 3 is given as 1100, we know T naught 2, Cp of gas is given as 1.147, mass flow rate of air is calculated as 14.64, and QCV, which is the calorific value, is given as 43 megajoule. So, m dot F turns out to be 0.261 kg per second. So, we can know now what is specific fuel consumption, that is m dot F upon F or upon T, and this gives us specific fuel consumption in terms of unit of hour as 0.138 kg per Newton hour, where we have multiplied m dot F by T into 3600. Having said this, this is the method to calculate the examples or to solve the examples for the turbojet engine. Thank you.